Hello, dear students. Welcome back to Exam Prep Tool. So we'll continue with the lecture from the last what we were discussing within linear regression. So I hope you remember that how we calculated the error over there. Now we'll be going further talking about how do we optimize that. Okay, and we have already done all those things for simple linear regression, but this time we were going ahead with more like multivariate or basically multiple linear regression. So we'll continue from there only. I hope you learned it, you enjoyed that. Okay, if you are enjoying these, please share it with your friends as well, and so that everyone can get benefit. So we'll continue from where we actually left. Let me just share my screen and we'll get started from there only. So yeah, I hope my screen is visible. So if you remember, I'll just write down these equation what we had last time as well, that we wrote something like this, that y bar for us is going to be equal to xw. Okay, and the other way we were also writing was like, if I talk about for one data point itself, my yi cap would be equal to like w transpose xi cap I can write, or I can also write it like, if I expand this thing further, like considering, let's suppose I'm having just three features, and the first feature I'm calling is xi 0th column. I means the row, and zero, like the other part is telling me the column. So something like this. Okay, so I hope we are clear until this point. This is what we all talked about, and we had something extra which is called the error function as well, uh, which is also called the loss function. I hope you remember. If I use on like a per data point basis, we write it like this: the sum of squared errors. So it would be nothing but yi minus yi cap square, and summation of this going from I equals 1 to your n, the number of data points. And if I would like to write it in terms of something like this, where I'm directly having the column given to me, so I would like to say my j is going to be, in that case, sorry, I guess it's my pen misbehaving over here with me. So expect that problem, but we'll handle it beautifully, need not worry. So j is equal to, in that case, what would it be? So now it's going to be a vector. Now corresponding to a vector, so let me just show you this. How would it like look like? So let me again, it's actually doing the same thing for the ease. Let me just write that over here. So it's something like this. So like if I, let's say this is capital Y, this is capital yi cap. So it's like this: 2.3, 3.4, 4, 9, and similarly you have a number of things over here. I know like you might not be able to see. Let me just take it a little up. Yeah, now you can see. So let's say over here you predicted 2, over here you predicted 3.5, corresponding to 4 you predicted 3, corresponding to 9 you predicted 10.5, something like this. So you can see now your capital Y and capital Y cap would be a proper vector. Now if you want to do something like this only, so you should take subtraction of these, and then whatever you are getting subtraction, you'll be getting a new vector. Now whatever is the new vector, norm of that would be giving you the same thing which you calculate over here. Right now, what was this? It was sum of squared errors. So error for each, square of that, sum of that. If you subtract this, now you'll be getting a vector. So it's like 2.3 minus 2 would be something like 0.3, over here minus 0.1, over here it's again same thing which is happening. Let me just try. Yeah, over here it would be 4 minus 3 is 1 only. Over here it would be 9 minus 10 minus 1.5. Yeah, something like this. So now you're having this. Now you want a square of this plus square of this plus square of this plus square of this. How do you get that? So if you have a vector, if you calculate a norm, it actually takes the square of each of its component and take a root. But instead of root, I don't want that. I want a normal square only. So what do I need? I just need simple norm square. So how would I write over here? This one would be written like this: y minus y cap. Sorry. So my pad, like this writing pad, is actually not behaving well. Sorry, my bad. Let's pick up this one only. So what I'll be having is, sorry, it would be yi cap and then norm, but square of that. So whatever you're getting over here, the same expression would be basically same value would be returned by this. So I hope you can see both ways how we are going to calculate our sum of squared errors, or the error or the loss function. Okay, now if this is clear, now I'll tell you how do we actually calculate it. And there are two important ways to actually find out what is the solution to this. Okay, there is third method as well, in which I can just open up everything, but that would be too much for this introductory lecture. If you want to learn that part, you can get into the paid course and you'll get to learn all that part as well. But over here, just for the understanding purpose, I'll just like briefly walk you through the two method which you can use to actually derive that expression optimal for the optimal value of w, which solves our linear regression problem. Okay, so I'll start with the first one, which is the easier one. So first method, so we already know that we are having something like this. So right now I'm saying y bar equals xw. Now, if I do not go by the idea of the calculus and all, what I want to say is whatever is going to be my y bar, that should be equal to y. So indirectly, what I'm saying is something like this, that my x bar should actually be equal to y only. This is what I'm considering right now. Okay, that if I find a perfect solution or a good solution using w, in that case, xw should be equal to your y. This is what we already know. Now, if I just write the dimension, which actually helps us understand something very important over here, what is the dimension of this? This is n into d. What is the dimension of this? D cross 1. What is the dimension of this? N into 1. Now, you could have told, sir, if I want to find out W, and if W is my perfect solution, can't I write W, the optimal W? Let me just write W star is the optimal one, such that if I multiply W star with X, I should be getting my Y only. So W star should be equal to X inverse Y. You should be telling me this. But the point is, we can't really say this. A simple reason for this being that my X is not a square matrix, it's a rectangular matrix. So we have a trouble here. Now, how do we convert a rectangular matrix to a square matrix? Can we do something about this? So if you know that if my X is a rectangular matrix, I can create something with the help of X itself. I can create two kind of square matrices. One can be X transpose X, other can be, again the same thing happened, but it's okay. We'll just handle it beautifully, easily, with calm composure. Other would be X into X transpose. So both you'll find are going to be your square matrices. But what we need over here is, you actually know that already. So if I write once again over here, this one, same thing. Okay. If I just write that same thing over here, what I'll be having is, please bear up with me for this lecture with respect to this issue, what I'm having. So we have X over here. Yeah. So this was, sorry. Let me just bring up the same pen. Let's see. Okay, I'll write. I'll just handle it. Okay, this was x inverse. That's something which we wanted, but we do not really have. What we have is, I would like to show that we have x w equals y equals y we have. Okay, please bear up with this writing problem what I'm having right now. Xw equals y. Now this is already something which is having rectangular matrix. Now how can I bring something square matrix? So I need to convert this side into the square. How would I convert? I will pre-multiply on both the sides by x transpose. So if I'll do that, what I'll be getting is simple thing. If I just multiply by that, I'll be getting x transpose over here. I'll be getting x transpose over here. So overall equation becomes x transpose xw into x transpose y. I hope you can see. And from here, now this is a proper square matrix. Now you can see w should be equal to, w optimal should be equal to x transpose x inverse, the same thing, inverse into x transpose y. And this is the normal solution of your multilinear regression problem. Okay, this is one way. I hope you could understand. Easy way just to understand how can we get it. The other way is actually using a proper calculus method. So let's get to that as well. Second method to actually prove that same thing using calculus. So by now, I hope you remember that my j is equal to what we talked about. We said my j was equal to actually y minus y cap and this one. Okay, now I hope you know that we can also write it like this, y minus y cap, because these were nothing but some vector. I can write it like this from simple linear algebra only. Okay, because a transpose a is nothing but a norm square. Okay, so what I am getting is this one. Now if I just open it up, what is my this part? Again, same issue, need not worry, we'll solve it. In between we are having, but yeah, it's okay, we'll deal with it anyhow. Okay, so what we had was xw transpose y minus xw. So if I take the transpose, what will be happening is I'll get y transpose. For the multiplication, if I do the transpose, what happens is their order changes. So it would become w transpose x transpose into y minus xw. Okay, so I'll go to the next slide. What I'm getting right now over here is j equals y transpose minus w transpose x transpose into y minus xw. If I just multiply these two terms together, what I'll be getting is y transpose y minus y transpose xw minus w transpose x transpose y plus w transpose x transpose xw. Now this is your j. Now, if you understand simple like calculus, so I would not get into the details, because my point over here is to make you understand how do we get that normality thing with respect to the calculus now. Okay, I will not get into the how do we calculate the derivative of matrices and all that requires some extra part over there. But I'll help you understand how easy it is if you know the basic calculus also. Okay. So now what do we want is j over here is a number and all these are vectors. Y is a vector, x is a matrix, w is a vector. I hope you can see this. We already know that. And what do I want? I want to find optimal w. So I should be taking a derivative of a number, a scalar value, a j would be a number with respect to a vector w. So that means my del j by del w or whatever it is, is it going to be a vector, matrix? You'll get to know, need not worry. But it should be something which actually tells you about that how your j varies with respect to the w. J is a number, w is a vector. One number, how does it vary with respect to a vector? That means the component of vectors. That means if I'm taking a derivative of a scalar value, a simple number with respect to three numbers, because my w was a vector of three numbers, with respect to three numbers, in that case, while taking a derivative, what I shall be getting is a vector of three numbers only, and each of these number would be telling that how j changes with respect to the first component, second number will be telling how j changes with respect to the second number, and so on. So like, just telling you over here that if I'm taking the derivative, it should be something like this: 1, 2, and this is going to be this vector I'm talking about. That means it is going to be a vector of three components if I take with respect to w. So that means, I hope now you are clear that if I'll be taking the derivative of j with respect to this w, which is a vector, just giving you that intuition only, I would like to say this is going to be a vector, okay, with three values. Just giving you the intuition, okay. Now, what would be happening on this side? It's easy without even getting to know the details if you understand calculus a little better. See, this part is completely independent of your, this part is completely independent of w. So that means, I hope, like as we normally talk about in calculus, something like this. Let me just write. So if I'm having, let me write three expressions so that you understand that better. S, again, this thing is happening, but just bear it with me for this. Let's suppose your A is equal to something like this. Ax square plus bx plus c. Now, if you want to take a derivative with respect to c, with respect to x, derivative of a with respect to x, what you will be getting is 2ax plus b, and derivative of c would be 0. Derivative of this was x was cancelled, only b was there. This was x square, so derivative of x square is 2x, so 2x. So I hope you know this much. You need to use the same thing. Now, because you're taking derivative with respect to the w, this will become a constant. So while taking the derivative, you'll not get something from this while taking del j by w, just giving you the idea. While taking with respect to this, you're having just w over here. So that means what you shall be getting is, again, you should just get rid of w now. So you should get a term of y or x only. Now, what should be the dimension of that? As I talked about this also, it should be coming out to be 3 cross 1, or basically whatever was your feature into one, number of features into one. You should be getting that. Would you be getting? So you need to rearrange corresponding to that. If you are good at it, you'll be getting that, okay. Or you need to know like the proper matrix calculus. So if I just avoid it, I shall be getting a dimension of t cross 1 or 3 cross 1. What was y? Can you remember what was the dimension of this? This was d, sorry, n cross d. This was your 1 cross what? N. So if you can see, this was overall giving you 1 cross d also already, but you wanted d cross 1. So what you shall be getting is, after taking derivative of this one with respect to w, must be some transpose of this one itself. So that means it should be rather x transpose y, rather than writing just minus of y transpose x. Minus is normally like you are just getting rid of w, you should be getting this term, but you need to take care of the dimensions, as I told you already about this, that it should be d cross 1. So you have to get d cross 1 dimension over here, okay. So this expression, same over here, you are getting rid of some w term also over here, be it transpose or whatever, but whatever term after getting rid of w you shall be getting is a vector again of dimension d cross 1. So you will again be getting x transpose y only over here, because it was already in that shape because of, like the proper arrangement of this. What about this one? So isn't it like you're having one matrix over here which is a square matrix, and then w transpose w, w transpose w, just treat it as like you're having two w's, so it's kind of a square only, w square. So what you'll be getting out of w square? 2w into whatever constant you already had. So it should be something like 2ax, where a is a your like a constant over here. treated like a simple matrix over here. So what you will be getting is plus 2 times of x transpose x w only. Now this is your expression. Now similar thing, whenever you're optimizing, you want to take a derivative and put it to 0. So you'll put it to 0. The moment you put it to 0, what you are getting is, I hope you can see, twice of x transpose y is equal to twice of x transpose xw. From here also you can see again, your w should be equal to x transpose x inverse x transpose y. And this is our solution which we talked about. So I hope we are clear both the ways, using the calculus, using basic understanding also, how we can find this normality solution. Okay, now there is what should I say, like a solution because of regularization as well, for which you need some extra clarity over there, some extra sessions over there, which is not possible out of this particular lecture. Okay, so this was all about getting to know about the solution of multiple linear regression, which is going to be, if you have your features, if you have your y values, you can always find out optimal w using this equation, which is going to be x transpose x inverse x transpose y. This is going to give you the final solution. Okay, using the normality idea. Okay, there is other way as well, which is gradient descent. Again, out of scope of this lecture, just telling you that what extra things we are having. L1 regularization solution, L2 regularization solution. Can we use in both of those cases such kind of a normal solution? The answer is no. In one of those only, you can just find it out, or you can just enroll for that to know how do we find out normal solution for one of those, and which one is exactly that particular case for the regularization. Apart from that, the most important next thing which I wanted to talk about was assumptions in linear regression. Very important to understand. Assumptions in linear regression. What are the assumptions? Okay, so we'll talk about that only. So let me just write down what are those assumptions we are having. We'll talk about each one of these one by one. So let me first of all write down all our uh, assumptions what we are having. First one is uh, yeah, the basic one, linearity. Again, the problem. Okay, we sorted from this end. Let's just write it out. So after linearity, the other one is normality of error. The third one is homoscedasticity. These seems to be very difficult terms, but these are not, once you understand better. Sorry, like having that issue only. Homoscedasticity. Homoscedasticity. HOMOSKEDASTICTY. The normal spelling of city. And the last one, which is no autocorrelation. Autocorrelation. Okay. So linearity tells me that whatever is going to be my true hypothesis function or my prediction, that is going to be always a linear combination of my feature itself, because that's why we write our solution as something like this: w naught into x naught plus w1 into x1 plus w2 into x2, something like this. I'm not talking about the fee like number of data points, but I'm just telling, if you just tell me one of the data point where x0 is the first feature, x1 is the second feature, x2 is the third feature, then in that case we write our solution like this. So we are saying that our prediction function or the hypothesis function can be expressed in the linear combination of our feature values or feature columns, whatever we are having, okay, feature dimensions. So it should be a linear function of my input data, which is my features, okay. What is the second point? Normality of error. So normality of error tells me that if I do this one, like so I'll be getting this vector, which is nothing but, for me it's going to be a vector only, a vector only. Now if I just look at the distribution of this error distribution, what I shall be getting is it should be a normal distribution. That means, for an example, let me just draw this simple line over here to help you understand. So let's suppose ideally the line which is fitting is this one, okay? And I know my data points were here and there around it, okay? Most of the data points would be on this line only, but some can be a little far also, possibly very far also, but the farther ones would be very rare, okay? So this normality of error tells me that if I'll calculate the error with respect to what I predicted and what was the actual value, what I'll find is most of the times my error would be having like my like, what should I say? That should, the error itself should follow a normal distribution, something like this. Okay, now what does it mean? That somewhere I will be having like, like some of the errors which might be because of outliers would be very rare cases. That means finding those kind of error value would be very rare. Something like getting some error because of this, something error because of this. So you can see there are just 2 points leading to this kind of an error, or for this I might have points, little extra points than these two only. Okay, so most of the time what you'll be getting is the errors because of the points which are lying closer only. So that means if you just look at the distribution means if you just get to see that what are the error values, you'll see some of the error values are actually repeating most of the time, or are most of the error values are lying in some particular range where I'm getting, like, I can always predict that, oh, this is going to be most of my error, most of the time this is going to be my error, okay, telling me that it would follow a normal distribution where I would say that, oh, that let's suppose my error I was saying was something like this only, uh, 0 to let's suppose some 100. So I'm saying most of the time my error is lying between some 30 to 40 only, or 40 to 50 only, 50 to 55, let's suppose. This is where my most of the errors lie. And then as I go on the left hand side, that means I'm having zero error. That is also very rare. And I'm getting something like like completely very high error. That is also very rare, because I'm saying I would be very close to these data points, but maybe the zero error itself can be something which would be very rare for me. Okay, so something like this would be there, in which I would be saying that most of the time if I plot the distribution, I'll be finding a range where I would say that, okay, this is most of the time my significant error. Then like less than that, I'll be having very less number of chances that I'll be getting this error, and more than that also I'm getting very less chance that that is going to be my error. Okay, normality, that is normality of error. Basically the error over here would be following the normal distribution. Third point, what is homoscedasticity? So homoscedasticity actually talks about variance of error with respect to levels of features. So, or you can say the scale of features. Not exactly scale, I should not say. I'll tell you. For an example, let's suppose x1 is one of the feature. Okay, so we know, like, we are having x1 as one of the feature over here. And this is my linear regression line I'm fitting, and something like this I'm saying. This is the overall variation of the error I'm telling you. So can you see that as my x1 value were lesser, I was getting error within this particular area only. As I'm increasing my x1 value, the overall variation within my variation within my error is increasing. Error would be how far I am from my like actual values. Okay, so this the homoscedasticity says that it should not be the case, because this example is of heteroscedasticity. This example is of heteroscedasticity. That means as the scale or the level of my feature changes, as it is increasing, my variance is also increasing. Or there can be opposite case as well, where my variance is decreasing. Homoscedasticity says that it should be independent. It should not depend upon the scale of my features. That means overall my the variance of my error should be something like this only. So if this was my line, I know my distribution, my variance of the error would be same throughout my scale of the features. It should not neither contract or neither expand as we move ahead or go back. Okay, so my overall variance of error should be lying in between this only. It should not expand, it should not like decrease. Now what does it tell? So if I increase the feature values, because of that, if variance is increasing, in that case we will not be able to use linear regression properly. Okay, it would not really be a best solution we will be getting in that case. So linear regression, like these assumptions are telling, if these assumptions are true, if that is the true case we are getting, in that case only we can have a proper linear regression giving me the optimal solution kind of a thing. Okay, now the next thing, we are clear with homoscedasticity as well. No autocorrelation. No autocorrelation. Now what does it say? So I hope you know correlation is like to how two features are correlated, something like this. Autocorrelation means relation of something with itself kind of a thing. Now what do we mean by autocorrelation over here? Now the moment we say autocorrelation in linear regression, what are we talking about is we are talking about correlation of errors of data points. We are actually talking about correlation of error of data points. That means this should not exist. There should be no correlation of error of data points. That means the error in fifth data point should not determine what should be the error in the third data point. Error in 10th data point, whatever you are getting, that should not be able to help you in getting what should be the error in your third data point or fifth data point or 12th or 100th or any. So basically the error for each data point should be completely independent from each other. It should not like one error was able to determine what would be the error in the other one, or it should not dictate. So that's what that's what we mean over here, that there should be no correlation of error in between the data points. That means no auto correlation. That was our last assumption with respect to your linear regression. Now there comes up very important fifth kind of a what should I say, assumption as well, which is called multicollinearity. Whether it is truly an assumption of linear regression or it is something which is being used for some extra advantage from linear regression. Let me just hint out there interpretability. So giving you some hint that fifth one, that is multicollinearity, is not actually an assumption of your linear regression, but that is something you should make sure if you want to interpret your linear regression model. What do we mean by that? You can just get to know, like, and you can enroll in the overall paid course, and there we have a number of things out there to help you understand all these things. So that was all with respect to like what exactly is going to be the normal solution. How do we find it out? The next was, what are the assumptions? What do we mean by those assumptions? That was the overall idea of this particular session. I hope you have learned it. And thank you for bearing me for some of these writing pad issue. Okay, I hope you could understand, you could enjoy. If you love these lectures, you can share, again telling you, you can share it with your friends, or you can just contact me. uh, I'll be ready to help you with anything with respect to the machine learning. Okay, so that was all. That was it for this particular session. Over here, I would end this linear regression part with respect to the important lectures which help you understand what is it. I hope this makes a number of things clearer for you, that how does all this thing work with respect to the linear regression, what is actually the linear regression problem. In the next session, we'll be bringing another particular model from machine learning, which is important with respect to the GATE DS syllabus, and will help you understand that, demystify what exactly lies with that. That was all. Thank you guys for watching this session. Bye bye.